Hello everyone, in this video we're going to look into radioactivity. So in the last video we talked about the structure of an atom, and specifically we investigate the solar system model of an atom. We know that there is a nucleus in the center of every atom, and today we're going to look into what happens when this nucleus undergo a decay process and what are the particles that it releases following the decay. So we'll start off with introduction. For radioactive substance is a substance that decays by emitting radiation from its atomic nuclei. And there are two ways in which radioactive element can affect us. First is contamination. If you eat something that that has radioactive element on it, we say that we have been contaminated. And the other way is that this radioactive substance can hit our bodies, and that's when we receive a dose of radiation and we have been irradiated. So here are some of the sources of radiation. First one is from the air that we are breathing now. And the air is radioactive. It contains a radioactive gas called radon, which sits out from the Earth's surface from radioactive uranium rocks underground. The other thing is that because we stay in a home like that, we also take in radioactive substance from the ground, and because we use materials from the ground to build our houses. So radiation can also reach us via cosmic ray from the space. So that's they are all natural radiation source, and for artificial radiation source, it could be X-ray, gamma ray, and also medical and for radiographer and stuff in a nuclear power station. They also work with radiation. So in order to detect radiation, we can use this device called a Geiger counter. The unit to calculate how much radiation there are is called the count rate. The higher the count rate, the more radioactive particles there are. So let's look into the process of radioactive decay. Is when radiation coming out from them. So it is the process when an unstable nucleus. Remember, nuclear physics is about the studying of nucleus. So when an unstable nucleus give out radiation, it will then become more stable. And why will it become unstable at the first place? It could be due to they have too many protons, or that they have too many electrons. So radioactive decay is a random process, means you can't really manipulate it. It just happens. Nucleus just undergo the decay, and then you cannot affect its rate of decay by increasing the temperature and so on and so forth. So when after a nucleus undergo decay, it will release one of these three elements. It can be a combination too, but these are the three elements that it will release, and these three elements are also what we call the radiation. First one is alpha particle, beta particles, and gamma particles. And I have created a table to show their differences. This is how they look like, and their symbols. For alpha particles, we have learned in the last video, they have 2 protons and 2 neutrons. Beta particles basically an electrons. Gamma rays is just an electromagnetic radiation. Remember the electromagnetic spectrum. And their charge is positive because they have 2 protons, and for beta it's negative, and gamma is neutral. So what happens after nucleus emit these particles is that they will become another elements. Remember the equation that we learned? So what happens is that if they emit alpha or beta particles, the element will change, as I will show in the next few slides. So another way we can compare the 3 different radiation is from their penetrating power. So if you look at how this picture illustrates perfectly how different radioactive substance, they have different penetrating power. Alpha particle is the weakest. They can only travel past paper. Beta can travel until aluminum, and gamma ray can pass through lead. So for alpha particles, they are absorbed most easily. Therefore, they have very little penetrating power. They cannot penetrate through our skin. And as for beta, they can travel through air and paper, can be absorbed by metal like this, aluminum. And for gamma ray, it's most penetrating. That's why we use it for cancer treatment. It takes several centimeters of dense metal like lead to absorb it. So if you were to rank the penetrating power, gamma will be the first, beta second, alpha third. So that's when when we compare the penetrating power, another thing we can compare is their ionization power. So before that, let's look at their speed. You can see that gamma ray is the fastest and alpha particles is the slowest. And the mass, because they have more, there's more nucleons, it will be mass times proton times 4. And electrons, mass of electrons, gamma ray has no mass. The charge is depend on the number of protons they have. So for ionization, we learned from the last slide that alpha particle is the least penetrating. That's because they are the most strongly ionizing. They can be most easily absorbed, and they are able to ionize something easily because of the proton state they have. All right, so that's the description. And beta particle is less ionizing as compared to alpha particles because it's just an electrons, right? And they can travel further in air without getting absorbed. That's why they can travel past this paper. And as for gamma ray, it is uncharged. It is also least ionizing because it just can't ionize. It travels too fast and then it penetrates through something very quickly, very easily. So here, I just want to show you two processes which involve the release of alpha particles and beta particles. Start off with alpha decay. So you can see that one example is the element used is called americium. So once it undergoes alpha decay, it turns to uranium plus the helium particles with some energy. That's when I said when an element undergo alpha decay or beta decay, they turns to another element because of the extra particles that they produce. And again, you can compare the difference between the nucleon and also the proton number. They are the same before and after the reaction. So as for beta decay, is from, let's say, carbon and turn to another element plus electrons plus energy. So this is the beta particle. And at this point, you might ask, hey, I noticed that the number of protons increases after the reaction. And where does this proton and where does this electron come from? So that's because in this reaction, one of the neutron, they are being split into one proton and also one electrons. And that's the equation for that process. And this proton here contributed to the extra proton in the element, and then electrons is over here. And that explains how beta decay occurs and also its equation. And that's this part of the graph. It is the beta particle. So radiation may knock electrons out of atom. This means that ions are formed. This is a process called ionization, because once you knock this electron off, now proton will have higher proton number in the element, so it will be positively charged. That's called ionization, making an ion. So as radiation emitted by the nuclei of the radioactive substance causes ionization, it is also known as ionizing nuclear radiation, meaning the radiation process causes ionization. So there is another way we can tell. Let's say you are carrying out an experiment. You don't know which one is which. There are two experiments that we can carry out to identify whether this is an alpha particle, beta particles, or electromagnetic radiation. So if you look at this plate here, we have electrically charged plate. One is positive and negative. So because opposite charges attract each other, so without looking at the label, we know that the radiation substance that is attracted to the positive plate will be the beta ray, because beta ray is negatively charged. It is attracted to the positive plate, whereas the other plates here that is attracted to the negatively charged plate will be the alpha particle, because alpha particle is positively charged. And as for the the gamma ray, since it's not charged, therefore it's not going to be attracted. The other way we can tell is to put a magnet in between them. So what happened is that we have magnetic field, and then this alpha and beta particles, they have electric charge. So in other words, we have magnetic field, electric charge. We can then deduce the motion of where the radioactive substance will be going. And we learned this in chapter 20 when we learn about flaming left hand rule. So by using flaming left-hand rule, you can try that out. Just point your finger according to the magnetic field, north to south, and then alpha particles, electric current flow, and then you will find out that the direction of force that is exerted on the radioactive substance. So that's when flaming left-hand rule comes in. So now we have learned the 3 different types of radioactive particles. Let's look into how do we quantify how fast the nucleus will decay? And that's when we have the term called activity, the rate at which a radioactive source nuclei decay. So the activity of a source decreases with time, meaning as time goes by, it decays slower and slower. As nuclei decay and become stable, there are more unstable nuclei, so there are fewer decays per second. So in order to explain this sentence, just look into this here. So imagine that this is the element and their nucleus. So what happened here is that as more and more nucleus undergo decay, right? The rate of decay will get slower because there's less nuclei remaining. So that's basically what it means here. In fact, when I have a decay graph, you can see that the graph shows that the amount of radioactive substance decreased rapidly at first, and then more and more slowly. In fact, the graph tails off slowly, more and more slowly. We cannot say when the last atom will decay. So different radioactive substance, they decay at different rates. So, but then how do we quantify how fast it is? We use the term half-life. Half-life of a radioactive isotope is the average time taken for half of the atom in a sample to decay, or the time for its activity to or current rate to half. So it doesn't mean that after 2 half-life, every atom will have decayed, and that's just not the case. I think a proper explanation would be like that. Imagine you have 16 atoms. What half-life means is that after a particular half-life, half of this atom, represented by the red color, will have decayed. And then on the other half life, the remaining atom, like 1, 2, 3, 4, 5, 6, 7, 8. So these are the remaining atoms. That half of this atom will decay. So it will leave 4. And then another half-life, you left 2, then 1. So that's more like the concept of half-life. Great. So let's do some work example. Strontium-90 has a half-life of 28 years. So that means they only decay after 28 years. The count rate of a sample is 480. How long will it take for the count rate to drop to 30? So we know that initially they have a count rate of 480. Remember, count rate is how we identify the radioactive substance. And after 28 years, half of them will decay, meaning now I'll have 240 count rate. Should be count per second, yeah. And then another 28 year, it will be 120. Another 28, it will be 60. And it's only after another 28 years, it will turn to 30. So you can see that we have undergo 4 28 years. So the answer should be 4 multiplied by 28. And that's how I show it. Therefore, the answer is that it takes 112 years for the count rate to drop to 30. Great. So when doing this type of question, do note that sometimes we also want to consider the background count rate. Remember, radiation source can come from the ground, the house, anywhere. So we need to consider the background count rate. So how we can get the corrected count rate of the substance is that whatever we measured, we minus the count rate, then this is our exact corrected count rate. So let's solve a question to understand it. The count rate of a radioactive material is measured, and the reading is 88, the background is 40, meaning the actual count rate of the substance is 88 minus 40, which is 48. And the half-life of the radioactive substance is 12 hours. What is the reading of the detector after 24? So we know that initially, we already know that it's 48. So this is the substance that will undergo decay. So after 12 hours, it will be 24. Another 12 hours, since we are looking at 24, it will be 12. So for the substance, it's 12 count rates per second. But of course, what the Geiger counter will show is they will include the background radiation. So whatever we calculated here, we need to plus back the 40 count rate from the natural radiation source. So whatever it will show 42 on the Geiger, 52 on the Geiger counter. All right, so that's about it. Oh, it's 12, but the correct answer should be 52. We need to plus 40. There's an error on my slide, and that's about it. Great. So let's look into some of the usages of radioisotopes. I will just go through this because I think they are self-explanatory. You can always read the slide. One usage of radioisotopes is smoke detector. How it works is that the smoke detector contains americium, which emits alpha particles. Therefore, these alpha particles will ionize air in the smoke detector. So if smoke comes in, it disrupts the ion flow, then the alarm will get triggered. So that's something that how radioisotope is used. Second example would be thickness measurement. We know that different elements have different penetrating power. First of foremost, alpha beta radiation is aimed at the paper. The amount of radiation that passed through the paper is detected, all right, measured by a sensor. So if the paper here is too thick, then it will absorb a lot of the beta particles and the reading will then be different. So the sensor will detect when there's an abnormal reading and then control the paper thickness accordingly. So here, beta radiation is used because alpha particles would have been absorbed by the paper here. It won't be detected by a sensor. And then for gamma ray, it will just pass through without much effect, even if this paper is very thick. So beta particle is the right choice. Cancer treatment, gamma ray is used to aim at the tumor. And then, so the technique ensures that other tissue receive only a minimum dose of radiation because gamma is they just target at the affected area. So cancer treatment is one of the usage. Food irradiation, gamma ray can also kill microprobes. So this results in sterile food, and this also ensures that the food is properly preserved. Sterilization of equipments, like what I said, similarly to what the food example here, they can be used to sterilize all the equipments. And for medicine, this is interesting. They are used to identify a blockage in the kidney. So the process involves injecting the patient with a radioactive chemical, and the scanner is used to trace the path of the chemical. The technique allowed for the detection of abnormal areas of growth, aiding in the diagnosis of disease. Because we can't see through what is inside our organs, so they inject this radioactive chemical. So for kidney blockage, they inject this specific element, and then if the kidney is blocked, the tracer will not pass through, indicating the presence of a blockage. And because why this is used is because they have very short half-life, meaning they will decay very quickly. It won't stay in the body for too long. So they are used in this example. And another one is engineering. It's very much like the tracing example. For engineering here, they just inject some radioactive materials into the pipe. And if there's a blockage in the pipe there, means that this radioactive elements will not pass through it. All right. So again, they allow them to track the flow of water and identify any pathway that could lead to contamination of local water supply. I'm just reading it because I think I couldn't explain much here. It will make the video very lengthy. So if you want to revise the subject using this slide, you can always purchase it on my website. All right, so another example usage of radioactive isotope is radiocarbon dating. It's not like a dating thing, but it's a technique that helps us to identify how long has, this object has been like a radioactive, like the dinosaur stone. So how it works is that because carbon is present in all living organisms, so when an organism die, the carbon-14 will begin to decay. So by looking at how much carbon-14 is inside a particular organism, we will know how long has this organism died, because we know how the half-life of this substance, right? So they basically help us to identify how long a living organism has passed away, like a dinosaur, right? So you can read it. So of course, there are some safety precautions when it comes to using these elements. because there are three ways that radiation can damage living cell. They can kill a cell. They could also cause cancer by mutating by the DNA mutation, because if you learn biology, radiation could cause uncontrollable mitosis. Right? They also change your gene, which leads to a different generation. So yeah. So the changed DNA will affect your offspring. Great. So the alpha particles here, they said it is less likely to harm us, but then if it enters our body, then we will probably it will probably lead to the development of lung cancer. It can't hurt us on the outside because it's not very penetrating. So some safety precautions for workers working in a area that has a lot of radioactive elements: just wear a suit, put in label to remind people, and then photographic foam domestic for badges. They track how much radiation someone is exposed to. So if the value get too high, then probably you have to walk away. Record keeping, right? That's pretty straightforward. Remote operating of scanners. So calculate the distance between them and the radiation source. Storage box for sources so that radiation won't leak out of the box. So let's try to solve some past year question. All right, a student carried out an experiment to find out the half-life of radioactive substance. Their results are shown in the table here. What is the half-life of this substance? So remember, half-life is the amount of time for this element to decrease by half. So we need to figure at what point it reaches half of the original count rate, which is 150. So you can see that it takes 40 seconds. Therefore, the half-life is 40. B. Second question, we have looked at this diagram later already. X, it can only pass through paper. It can't even pass through paper. Therefore, it will be alpha particles. C and D are incorrect. And for Y, it can pass through everything. Therefore, Y should be a gamma ray. And for Z, it can only pass through aluminum. So it should be beta particles. My answer should be A. So that's, oops. Oh, wait, sorry. Yeah, I make a mistake here. Should be, the Y here should be beta gamma ray. So my answer should be B. All right, Y. Great. Next one. Which statement is not a method used to minimize the risk? So store the sources in a lead line box. That's correct. Proper storage. Minimize the amount of time spent handling. Yeah, that's correct. Keep the source cool. That's not correct, because we know that radioactive decay, the process cannot be manipulated by temperature. So my answer is C. Great. So next one, radioactive sources are used in manufacturing process. The diagram show how radiation used to measure the thickness. Okay, so for this one, we know that the answer is beta particles. That's something that we learned, because for gamma ray, it will just pass through it. It will make no difference to whether the aluminum is thick or not. An alpha particle will just be absorbed, so that it will not be suitable. So next one, a nucleus of uranium undergo and emit an alpha particles. Which equation correctly describe this process? It's already mentioned in when we compare the three radioactive particles, right? So initially it's uranium, turn to the helium. No, not helium, but alpha particles. For this, in order to know what is the correct answer, we just need to look into the element. It doesn't, for uranium, this is confirmed not correct, because they are the same. This is the same element. This is not what we want. And then for uranium decay, they also do not need to be combined with in alpha particles. That's also incorrect. And for the fourth answer, it's either the number 4 or D or A. If you look at D, right, the number of protons does not, when they add up, 2 plus 88 will be equal to 90, and it doesn't match 92. So the correct answer should be A, in which the proton number before and after the reaction matches left and right hand side. So A. So next one, the last question, a radioactive substance has a half-life of 4 days. it emits 8,000 particles per minute. How many particles will it emit per minute after 12 days? So it has a half-life of 4 days, meaning after 4 days, it will be 4,000. After 8 days, another 4 days will be 2,000. Since we're looking at 12 days, just do another one, 1,000. So the answer should be C. And that's it. And that's about it for this chapter. So in this video, we have compare and contrast the different radioactive substance, alpha, beta, and gamma. And let me know if you have any question in the comment section, and I will try my best to help you. Thank you so much for watching. See you in the next video.